Imagine a time when the universe was a dark space, an era before the first stars lit up the heavens. A period known appropriately as the Dark Ages. It was a time when the cosmos lay shrouded in a cloak of mystery, filled with neutral hydrogen gas that hid the light, making the universe invisible to itself. But in this darkness, the seeds of change were sown. A pivotal event loomed on the horizon that would end the cosmic silence and usher in the epoch known as reionization. This transformative epoch remains one of the greatest mysteries since the Big Bang. The James Webb Space Telescope set out into the great unknown on a mission to unravel those very mysteries. Breaking through the veil of cosmic dawn, it offers us today a glimpse of an age when the universe awoke from darkness. What secrets are hidden in the light of the first galaxies? What forces ended the reign of the Dark Ages and heralded the beginning of reionization? And most importantly, how did these discoveries confirm or refute our theories of early expansion and the formation of cosmic structures? Join our journey to the very edge of space and time to trace the path of light back to its origins together. Just moments after the fiery birth of the universe in the Big Bang, the reality we know was unrecognizable. The newborn universe was a boiling cauldron of hot, dense plasma, a turbulent sea of subatomic particles colliding and combining in the extreme energies of the early cosmos. As the universe expanded, a cosmic interaction emerged in which matter and energy were linked by the rhythms of the nascent laws of physics. Expansion led to cooling, and within a few 100,000 years a transformation took place. Protons and electrons, once too energetic to bind, fused together to form the first neutral hydrogen atoms, casting a veil of darkness over the cosmos. This event marked the transition of the universe from a plasma state to a gas state, which led to the appearance of the cosmic microwave background, the first light of the universe, the faint afterglow of creation that can still be observed today. But along with this first light came the cosmic Dark Ages. Imagine a universe devoid of stars, where galaxies have not yet formed. A vast expanse of darkness pervaded only by the faint glow of the cosmic microwave background. Such was the universe during the Dark Ages, when light-emitting objects were absent and the all-pervasive neutral hydrogen gas formed a cosmic fog, absorbing any light that could ionize it. But in this darkness, the groundwork was laid for cosmic transformation. Dense clusters of gas began to gravitate toward each other, slowly thickening under the inexorable pull of gravity. These were the first steps toward forming the cosmic structures we see today, the precursors to the stars and galaxies that would eventually break through the darkness of the Dark Ages. As we plumb the depths of the origins of the universe, we are reminded of the profound transformations that shaped the cosmos. The Dark Ages, a period characterized by darkness and silence, were only a prelude to the events that followed. As the universe moved forward in time, leaving behind the Dark Ages, a monumental transformation was looming on the cosmic horizon. This was the age of reionization, a pivotal chapter in the grand narrative of our universe. Reionization refers to the process by which the neutral hydrogen gas that filled the early universe was ionized by the first light sources, effectively lifting the cosmic veil of darkness and allowing the universe to once again shine with light. This process is an important phenomenon in the history of our universe because it represents one of the few ways in which we can indirectly study the earliest stars and galaxies. Imagine the universe in a transitional period characterized by an abrupt transition from opacity to transparency. In it, the ubiquitous neutral hydrogen gas that once absorbed all ionizing light began to change. tiny bubbles of ionized gas appeared as the first stars and galaxies formed, each becoming a cradle of light that pierced the surrounding darkness. These bubbles, at first few and isolated, began a journey of expansion and unification, marking the large-scale process of reionization that transformed the early universe. But what force was powerful enough to cause such a colossal change and gradually disperse this hydrogen fog? This question is at the heart of reionization, a mystery that astronomers and cosmologists have been piecing together clue by clue for decades. The prime suspects were the first luminous objects formed in the universe, the first stars and galaxies. These celestial formations, born from the gravitational collapse of dense regions in hydrogen gas, began to shine, their light making its way through the cosmic fog. According to the theory, the first stars were 30 to 300 times more massive than our Sun and millions of times brighter, burning for only a few million years before exploding as supernovae. Among these early stars, a special type known as population 3 stars, massive and incredibly bright, shone with a fierce light. Originally thought to be composed solely of hydrogen and helium, these stars were the first to break the cosmic silence. Their intense ultraviolet light was capable of splitting hydrogen atoms into electrons and protons. In other words, ionizing them. However, the history of reionization is characterized by complexity and nuance. As the bubbles of ionized gas grew and merged, the role of these early stars has come into question. Were they alone responsible for this cosmic transformation, or did other, more numerous and less luminous objects contribute to the process? The mystery deepened with the realization that the reionization process was not uniform, but discontinuous, with the ionization regions expanding at different rates and different directions. This diversity suggested a variety of sources, each of which made a unique contribution to the overall picture. This was the time when the universe underwent one of its most dramatic transformations, a period that allowed light to travel unimpeded across the vast expanse of space. This very moment was captured by the afterglow of the Big Bang, the cosmic microwave background, or CMB. The CMB serves as a relic snapshot of the universe in its infancy, giving us a glimpse of conditions at the dawn of cosmic reionization. After reionization in the cosmos, a fundamental question arises. What forces were powerful enough to end the cosmic dark ages and ignite the universe with light? The search for these driving forces leads us into the heart of the unknown. So as we discussed earlier, among the prime suspects are the elusive stars of population 3. These theoretical giants, composed entirely of hydrogen and helium, are thought to be the first stars to crack the primordial darkness. Their intense ultraviolet radiation, capable of ionizing huge masses of hydrogen gas, makes them formidable candidates for reionization. However, their unstable nature and lack of direct observational evidence cast a shadow of mystery on their role. Another group of potential culprits are quasars, the extremely luminous nuclei of early galaxies, powered by supermassive black holes. These cosmic beacons, with their intense radiation, could ionize hydrogen gas over vast distances, carving out large ionized regions in the intergalactic medium. But like puzzle pieces that don't quite fit together, the distribution and number of quasars cast doubt on their ability to fully explain the observed ubiquitous reionization. However, the keen eye of the James Webb Telescope discovered that in the early universe, the cosmos is teeming with faint but unexpectedly numerous galaxies. These galaxies, less massive and less luminous than their later counterparts, may have played a more significant role in reionization than previously thought. Their abundance and the cumulative effect of ionizing photons emanating from them could have contributed significantly to the transformation of the cosmic landscape. If this were the case, instead of a few dominant sources, reionization could have been caused by a multitude of stars and galaxies, ending the Dark Ages. So what has JWST discovered? In the dense cosmic galaxy cluster Abell 2744, also known as the Pandora cluster, a whole bunch of unremarkable dwarf galaxies have been uncovered. The luminosity of such galaxies is more than 100 times fainter than our Milky Way. Gravitational lensing played a crucial role in this study, acting as a cosmic magnifying glass. It allowed astronomers to observe and study extremely faint galaxies from the early universe that would otherwise have been invisible even to the very powerful Webb telescope. By warping the very fabric of space, the massive Pandora cluster amplified the light from distant galaxies, making them appear larger and brighter. In their study, thanks to this magnification effect, astronomers took and analyzed the spectra of 8 extremely dim galaxies. Such modest celestial formations, often overlooked in the cosmic timeline, have come to the fore, changing our understanding of the evolution of the early universe. This particular type of dwarf galaxy holds a surprising secret for its modest size. It emits huge amounts of ionizing radiation, 4 times larger than previously thought. Astronomers estimate that 50,000 sources of near-infrared light are present in the Webb image of the galaxy cluster, Abell 2744. To arrive at this conclusion, the team first combined data from ultra-deep JWST images with additional Hubble Space Telescope images of Abell 2744 to select extremely dim candidate galaxies in the epoch of reionization. The near-infrared spectrograph was then used to study the emission characteristics from the distant objects. This discovery changes the paradigm of our perception of the initiators of cosmic reionization. For the first time, scientists have reliably measured the density of such faint galaxies and successfully confirmed that they are the most abundant population during the epoch of reionization. Their ubiquitous presence and significant ultraviolet emission indicate that they may have played a more important role in the end of the Dark Ages and the formation of the ionized landscape of the universe than previously thought. What makes dwarf galaxies particularly intriguing is their potential for uniform ionization. Unlike the large isolated bubbles created by more massive galaxies or quasars, the ionized regions around dwarf galaxies were likely smaller and more numerous, thus weaving together the complex network of light in the early universe. This complex structure of ionization, with countless small bubbles thickening with time, paints a picture of reionization that's more gradual and widespread than previously thought. A similar, unusual family of dwarf galaxies was actually discovered back in the last century, in the mid-1920s, the so-called green pea galaxies. However, it took scientists a long time to explain what they are, having unambiguously determined only in 2023. These galaxies got their name for their compact size and green glow in optical images. Green peas are characterized by an amazing ultraviolet luminosity, indicating active star formation and the enormous amount of ionizing radiation they emit. These galaxies, although small in size, play a colossal role in the history of cosmic reionization. The James Webb Space Telescope has shed new light on these enigmatic galaxies, revealing their architectural legacy on the canvas of cosmic evolution. Along with galaxies such as Harrow 11, known for their intense ultraviolet emission, the green pea serves as a living laboratory, allowing us to observe ionization mechanisms in action and further confirming the conclusions of a previous study. Not the least of these studies is the theory of cosmic inflation, a sharp and rapid expansion that's believed to have occurred a fraction of a second after the Big Bang. According to this theory, the universe underwent an exponential growth spurt that smoothed out all the initial irregularities and led to the homogeneous and isotropic universe observed in the cosmic microwave background. Looking into the epoch of reionization, JWST offers a unique vantage point to study these underlying theories. By observing the earliest galaxies and their distribution, we will be able to find echoes of inflationary fluctuations and assess their consistency with predictions. The distribution, size, and number of ionized regions created by the first galaxies and stars during reionization provide insight into the density fluctuations in the early universe that were amplified by inflation. Density fluctuations in the universe are like having a large room full of people with a little more people and a little more emptiness. Imagine the room is filled with people standing equidistant from each other. This is similar to the early universe, which was mostly homogeneous. However, in some parts of the room, groups of people may stand a little closer, creating crowding, while other places may be a little more empty. In the universe, these crowded and empty spaces are areas where there is a little more or a little less matter, stars, galaxies, and gas, than average. Over time, gravity pulls more matter into the crowded places, making them even more crowded, forming galaxies and galaxy clusters, and leaving the emptier areas even emptier as gaps between the crowded places. This is how the structure of the universe, with all its galaxies and vast empty spaces, emerged from these initial small differences in the distribution of matter. According to this model, such masses such as the first stars and dwarf galaxies formed first, which gradually merged to form the grand galactic structures we see today. Such nuances lead us to reflect on the complexities of the expansion of the early universe and to ask critical questions in the future research. How do these observations of the reionization epoch fit with predictions of cosmic inflation? Do they support a model of hierarchical structure formation, or do they suggest refinements to our current understanding? A future web observing program called Glimpse will provide scientists with the deepest images of the sky in observational history, opening new windows into the earliest epochs of the universe. The study seeks to detect even fainter galaxies from the epoch of reionization. By targeting another galaxy cluster, Abel S1063, these observations will expand our cosmic census, potentially confirming the typicality of the dwarf galaxies observed in the current study and offering further insight into the large-scale distribution of galaxies in the early universe. This next step in the study could refine our understanding of the period known as Cosmic Dawn and the appearance of the first galaxies, shedding more light on the formation of the universe and its grand evolution. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field. All these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason: it has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the Sun is just one node, a lone star among countless others. Close to the Sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our Sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special. just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our Sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the Sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the Sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the Sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the Sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the Sun. Although the Sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness, and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our Sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the Sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of the galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our Sun is now. But even stars like our Sun must face change. In about 5 billion years, the Sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our Sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel? There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, Their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter, a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? In the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals, in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles, because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1, which leads to repeated gravitational interactions at the same point of the particles' orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1 to 2, 2 to 3, or 3 to 4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to move to a different orbit, leaving the resonance gap-free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kuiper Belt, lies another fascinating story of celestial harmony. Neptune, the 8th planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the 9th, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3-to-2 resonance gravitational lock, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined. determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence. In the infinite depths of the universe lies a fundamental principle, as mysterious as it is omnipresent. This force governs the very fabric of existence, yet remains elusive to the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos. Here on Earth, entropy is evident in every rustling leaf, every rolling wave, and every moving cloud. It's the quiet organizer of natural processes, from the simplest to the most complex. But what is entropy really? It's a phenomenon often misunderstood as an ordinary disorder, but it's more than that. Entropy is a transformation, a movement from order to disorder, from concentration to dissipation. This is exactly why your coffee gets cold, why the ice melts, why the scent of flowers dissipates in the air. So let us understand how an order is hidden in what appears to be chaos, and how does this mysterious force shape our entire environment, from the smallest particle to the largest galaxy, and even the very course of life itself. There is a hidden force at work in every corner of our world, from the quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great work of the universe. Imagine a dewdrop on a leaf. shimmering in the morning sunlight. As the sun rises, the dewdrop slowly disappears, and its particles disperse into the air. This phenomenon illustrates a fundamental principle of nature, the transition from a concentrated state, the dewdrop, to a dispersed state, the water vapor in the air. At the molecular level, this principle manifests itself as the tendency of particles to move from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, moving from a structured gathering to random scattered groups. In the center of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour gradually fades away as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it's much more nuanced than that. It's about transformation and change. Like a sandcastle slowly crumbling under the merciless waves, entropy is the inevitable transition from order to disorder. This concept is encapsulated in the second law of thermodynamics, a fundamental principle of physics. It states that in any closed system, entropy will either remain constant or increase over time. In other words, the natural course of the universe is toward greater dispersion and disorder. From the grand scale of the cosmos, where stars and galaxies form and disappear, to the minutiae of our daily lives. This principle is a universal constant. It governs the birth and death of stars, the flow of rivers, and even the fading heat in a coffee cup. Imagine a steaming cup of coffee left on a table. Over time, its heat dissipates into the surrounding air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a more diffuse state, a cold room. Or take an ice cube melting on a warm day. The structured, solid form of ice turns into a puddle of water, whose molecules are free to move. This transition from a solid, ordered state to a fluid, disordered state is a classic example of increasing entropy. In every aspect of our universe, this quiet but relentless force is always present, subtly directing the flow of energy and matter. As we delve deeper into the theory, it's crucial to go back in time to the era when the concept first emerged. The history of entropy is intertwined with the minds of some of the most brilliant scientists in history. Our narrative begins with Sadi Carnot, a French physicist often referred to as the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His research laid the foundation for the laws of thermodynamics, which were later incorporated into the concept of entropy. Carnot's visionary work described how heat engines work and focused on how energy is transferred and transformed. His theories have played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our story is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. He built on Carnot's ideas by delving into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot spontaneously transfer from a colder body to a hotter one, the principle underlying the second law of thermodynamics. His mathematical formulation of this concept allowed it to be quantified, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was groundbreaking. He showed that entropy can be understood as a measure of disorder at the molecular level. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, gave a profound insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundation for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. Turning our gaze to the natural world, we find that entropy is at work in every ecosystem, shaping the environment and the life within it. Nature, in its infinite complexity, is a vivid canvas of disorder in action. Consider a fallen tree in the forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi break it down, returning nutrients to the soil. This process of decay and renewal is a manifestation of our principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting through rock and soil, and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of the role of this principle in geophysical processes. Weather is another area in which chaos plays a crucial role. Cloud formation, rainfall, snowmelt. These are all processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy is manifested in the life cycles of marine ecosystems. Coral reefs, for example, thrive on the delicate balance of nutrient cycles, temperature, and ocean currents governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight into energy, is another interesting example. Here, the entropy principle plays a role in converting solar energy into chemical energy, a process fundamental to life on Earth. From the tiniest interactions of microscopic organisms to the grandeur of ecological systems, this fundamental force is the invisible conductor of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which chaos and order coexist in a delicate balance. Consider the simple process of seed germination. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from the environment, converting it into structured, organized forms. However, there's a price to pay for this organization, an increase in the overall disorderliness of the system. In the human body, entropy is our constant companion. Our cells are energy conversion power plants, constantly converting nutrients into energy. This metabolic activity is vital to our existence, but it also leads to increased disorder as energy is released in the form of heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates the role of entropy in ecological processes. Each transfer of energy from one organism to another involves energy dissipation, contributing to the overall disorder of the ecosystem. Looking at the bigger picture, the evolution of life on Earth can be seen as a journey through entropy, from the first single-celled organisms to the complex network of life we see today. Evolution has been a process of increasing complexity, driven by the fundamental laws of energy and matter. In the grand narrative of life, entropy is not just a concept of decay or disorder. It's the driving force behind growth, complexity, and a constant cycle of transformation. Life in all its forms thrives in the delicate balance between order and chaos, a testament to the profound interplay of energy and matter. In the cosmic arena, the principles governing entropy show a universe in constant motion, a stage in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics. Inside nebula, clouds of gas and dust collapse under gravity, heating up and eventually triggering nuclear fusion. It's a transition from potential energy to kinetic energy, a cosmic example of energy distribution on an enormous scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovae, dispersing their elements across the cosmos. This dispersion is a powerful demonstration of the universe's tendency to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have such a strong gravitational pull that even light cannot escape them, play a significant role in the energy dynamics of the universe. The black hole event horizon marks the point of no return, where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is itself a confirmation of these principles. Galaxies are diverging, energy is becoming more evenly distributed over vast space, and the fabric of the cosmos is stretching, all of which indicate that the universe is evolving toward a state of higher dispersion. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the early universe. As we know, this radiation is a remnant of a time when the universe was hot, dense, and in a lower entropy state. Paradoxically, as the universe expanded and cooled, its randomness increased. And this is what led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the heat death of the universe. In this scenario, the universe reaches a state of maximum entropy, where all energy is distributed so uniformly that further energy transformations become impossible. This is a future in which the universe is cold, dark, and devoid of the energetic dynamics that drive cosmic evolution. In this vast cosmic action, the flow and transformation of energy shapes not only the stars and galaxies, but also the very destiny of the universe. It is a continuous process of creation, transformation, and ultimately, disintegration. In the modern world, the concept of entropy has transcended its scientific origins, finding applications in a variety of fields, but subject to common misconceptions. Currently, entropy plays a crucial role in the development of advanced technologies. In the field of renewable energy, a thorough understanding of this concept is essential to improve the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge greatly helps in optimizing the conversion of natural energy sources into usable energy. In the field of information theory, entropy has acquired a new meaning. It represents a measure of uncertainty or randomness in a system. This concept is crucial in data encryption and compression, where controlling and predicting information patterns is essential. Despite its scientific importance, entropy is often misinterpreted. A common misconception is to equate entropy solely with disorder or chaos. Meanwhile, while the definition that entropy leads to an increase in disorder is correct, it is worth clarifying that we're talking about the distribution of energy and the probability of certain states. Another misconception is the notion that entropy can be reversed or overcome. In popular culture, we see images of time reversal or spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Modern physics research is considering its impact on quantum mechanics, the behavior of black holes, and the ultimate fate of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand urban development patterns. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be critical in addressing them. Whether it is advancing technology, exploring space, or managing our planet and conserving its resources, entropy remains a fundamental concept that will continue to define our journey into the unknown.